I'm very happy to introduce Professor Neil Robertson, who comes to us from the University of Edinburgh. And he works in materials chemistry for energy and electronic applications. He graduated with both BSc and PhD from the University of Edinburgh, and he is currently the Energy Technology Partnership Team Leader for Solar for Scotland. And he's also currently an associate editor for the Royal School of Chemistry Journal of Materials Chemistry and the Director of Internationalization for the School of Chemistry, building research partnerships across Asia, Europe, and America. And he's interested to discuss and learn more about the societal context of rural energy uptake to balance his background in the physical sciences. We are very happy to have him here at A3, and I'll hand over now to Neil.
So thank you very much, Shika, for the introduction, and thanks also for the opportunity to come here and visit and meet everyone and just have really interesting discussions today. It's a real privilege to be here. I've been to India many times in the past, but to a limited number of institutions, mainly talking to chemists and physicists and engineers, and it's great to come here and talk to such a wide variety of people with different backgrounds. So I'm really enjoying it, and hopefully it can be very useful as well. I wasn't sure what to talk about because normally when I give talks, I'm talking about the details of materials chemistry, some quantum mechanics, electrons, things like that. And of course, that's not appropriate for a mixed audience. So I'm going to talk about solar power, which is the area we work in, but we work in the materials chemistry aspect. But I'll try to show you some of the developments that are taking place in photovoltaic technologies and in photocatalysis or water purification in a way that hopefully might be useful to you in terms of giving some perspective on how these fields are developing. So first of all, a wee bit of background about where I've come from. So I'm from the University of Edinburgh. So the city of Edinburgh is here, capital city of Scotland. So the UK, like India, is divided up into different states. The largest, of course, is England. Scotland is the next largest. However, the population of Scotland, which is the borders about here, so this is all Scotland. The population of Scotland, I learned today, is smaller than the increase in population of Bangalore over the past 10 or 12 years. So we have only 5 million people. So Edinburgh is a very attractive city. This is looking at the old town here. This is part of the old town. This is the new town. The new town is 200 years old, and both the old town and the new town are UNESCO World Heritage Sites. And actually, Edinburgh is also it was the first ever UNESCO City of Literature as well. So if you have the opportunity, you should definitely visit us. A few words about where I come from. I'm from the School of Chemistry. So chemistry in Edinburgh. So the university started in 1582. Chemistry started in 1713. So really at the beginnings of the field of chemistry, it was just emerging from the history of alchemy before that. We also have the oldest chemical society in the world, and we have some nice historical context. Joseph Black, this guy here, discovered carbon dioxide. So some really significant discoveries in the past. That's all history. Nowadays, in modern times, we have a partnership with St Andrews Chemistry Department, and together in 2014, the most recent research assessment, we were second in the UK. So the UK is a difficult place to come second, so it's quite a good achievement. And this guy here is Fraser Stoddard. He won the Nobel Prize for Chemistry last year. He's one of our alumni. He is a Scottish guy who went on to win the Nobel Prize after studying in Edinburgh. So lots of nice history and more modern achievements as well. So what I'm going to talk about is, first of all, a very brief background to energy and solar energy. I'm sure it's a very knowledgeable audience. You know most of these things, so I won't spend long on that. I'll then talk about emerging photovoltaic technologies to maybe give you a sense of how that field is changing. You're all familiar with silicon solar cells, but what are the technologies that are coming down the line that may influence things in the years to come? And then finally, my main theme and the things I've been having some discussions about today, photocatalytic water purification. First of all, just a bit of context about my own motivations and some of the wider things I'm trying to achieve. So in ISER Pune in September, we organised, or I was the main initiator of a UK, India and Newton Researchers Link workshop called Translating Clean Energy Research to Rural India. And the idea of this workshop was to bring together physical scientists and social scientists, because I still feel there's insufficient communication between those two disciplines. A place like Atri is a perfect example of that working in practice, but still it's relatively uncommon, and a large number of physical scientists and social scientists need to better get to know each other so they can tackle some of these bigger problems. So we brought together a mixed group from the UK and from India, from across physical sciences and social sciences. Satish Ogle and Isar Pune was our host, and Dr. Priyadarshini Karve from Samucha Envirotech, a social enterprise based in Pune, also helped facilitate and organize the visits. So that was our group. Some of you may recognize Shika in the middle. So that's where I met Shika, and that's what's facilitated my visit here today, or made that possible. So hiding in the middle there. As part of that workshop, we had some visits to villages, and we really learned an awful lot. I'm not so sure about the Indian participants, maybe they already knew a lot, but certainly the UK participants learned an awful lot about the reality of trying to introduce technology in villages, and how that has to be done according to the lifestyle, the social, political, economic, cultural, religious, historical aspects of the area, and not just the technology. So that was a really fascinating visit, from which we learned a lot. We also had some visiting expert speakers talking about some of the technology they had implemented in clean cooking and arsenic removal and other examples to show examples of how it was done. We had a lot of brainstorming and then a lot of project development through the day. And towards the end, we then got together and tried to formulate some project ideas. So this was all based around the need to bring together people from different disciplines to tackle some of these huge challenges that we face in energy, water, and related aspects. Okay, so that's a bit of a background about how I came to be here, and the direction of travel for me, coming from the purely physical sciences, dealing with materials chemistry in quite an abstract way, towards trying to put some of that knowledge into practice. And one of the real big resources I want to tap into is solar energy. And of course, everybody has an awareness of the importance of this, but just to put it into context, it's worth thinking about solar energy in comparison with other renewable forms of energy. So these slides are a few years old now, but approximately, slightly higher than this now, approximately the rate of energy usage in the globe is about 17 terawatts. So that's 17 terawatts of power constantly consumed by human civilization. And if you look at the theoretical upper limits of what different technologies can deliver, we can see that there's a gap. So ocean tides and currents, and this 2 terawatts value here is not a practical number. That's the upper theoretical limit. If you were to build barrages, etc., everywhere across the planet, you would get up to about 2 terawatts. Hydroelectric, if you were to dam every single river in the world and not care about the environmental consequences, you could get up to 3 terawatts. Wind, if you saturated all the available land area on planet Earth with wind turbines, forget about houses or anything else or people, just cover them in wind turbines, you could get about 4 terawatts. Geothermal, about 12 terawatts, so numbers are getting bigger, but that's then covering the entire surface of the planet with geothermal extraction. Photosynthesis looks better, 100 terawatts, but then of course, this is an upper theoretical limit. This means we no longer eat or have any biodiversity. We just cover the surface of the planet in energy crops in order to get this level of output. So the real practical numbers for these are much, much, much lower. So what we can see is that if we rely exclusively on these renewable energy resources, we can't reach this. We can't get there. It's not doable. What about solar energy in comparison? How much theoretical capacity is there in solar energy compared with these? Well, there's 120,000 terawatts. That's how much the Earth receives from the sun constantly. So clearly we can see that if we want to replace our dependence on fossil fuels with renewable energy, a massive proportion of that has to come from the sun because there's nowhere else. Now, I'm not being critical of any of these. These are all important. They'll all have an important role to play. But without solar energy, it can't be done. So solar energy must be the key player. What can we do with that solar energy? Well, we can make hot water. These are solar thermal panels for making hot water. Photocatalysis. Pilkingtons have developed a self-cleaning glass. So I'll be talking more about photocatalysis, not for cleaning glass, but for cleaning water later on. Water disinfection. So this is without any catalyst. This is just the UV rays killing bacteria in the water. Passive heating for growing plants or for keeping people warm. Of course, in India, you don't really need passive heating of houses, but passive cooling can be achieved as well, solar cooling. And of course, electricity using photovoltaic panels. So there's lots of different things we can do with solar energy. Sometimes this is the only one that gets any attention in the media and in business, but all of these other areas are also important and can play a big role in energy management as well as lifestyle quality. So with all of this going on in University of Edinburgh, there's a number of different people got solar interests. Mine are in materials for photovoltaics and photocatalysis. I'll talk about that shortly. But I have some colleagues who are also involved in other aspects. So for example, Andy Kerr directs the Edinburgh Centre for Carbon Innovation, which is this centre which is based on interpreting technical understanding for policy. So acting as an intermediary between the scientists and the government for developing policy in a scientifically informed way. And I believe that that type of activity also takes place here to some extent. The centre is really focused on that. My colleague Jamie Cross in Social and Political Sciences works on solar waste. Very many people are now introducing solar technologies to rural Africa, rural India. What happens at the end of its life? Is it just tossed into the nearest stream, or can there be some recycling or repairing that takes place? Large amounts of electronic waste are now being generated in rural areas, and that needs to be managed, and a life cycle system has to be developed. Thalia works in solar water purification, so I work closely with Thalia, and Giulio Santori works in solar thermal, not just solar heating, which we need, but also solar cooling, which would be of relevance to countries like India. So lots of solar activity taking place in Edinburgh. So you might say, why is somebody from Scotland interested in solar energy? We're from 56 degrees north. Here's Edinburgh here. For comparison, there's London down there. So below this line is England. This is all Scotland. This is Wales. This is Northern Ireland. So we're up here. And here's the solar radiation map. So this colour here for Edinburgh corresponds to around about 900 kilowatt hours per metre squared of radiation. Is that enough? Is that sufficient? Well, actually it is. This is my house, and here's the guys putting solar panels on the roof. So in my house, we can get nearly all of the domestic electricity that we use generated from our own roof. And that's at 56 degrees north. And even in Scotland, not quite yet, it will be cheaper than grid electricity. At the moment, that's already the case in India and many other parts of the world which are sunnier, but that will come to everyone eventually. With solar thermal, we don't have solar thermal. I'd like to install that next once my wife lets me. We should get about 40 to 50% of our hot water from solar as well. So it can provide a lot even in Scotland. What about India? Well, if you look at this scale, you can't read that from here, but looking at Bangalore, you're up more around about over 2,000 kilowatt hours per metre squared, more than twice what I get on my roof. And even on my roof, I can supply all my electricity supply just from the roof. So think what can be achieved here. Of course, that's well understood in India. There's now a big government focus on this. About 300 clear sunny days per year. We don't get that. About 20 gigawatt installed capacity at present, with an ambition to head towards about 100 gigawatt installed capacity. So massive increase. The biggest single plant at the moment is in Andhra Pradesh, about 1 gigawatt. And of course, that's all aimed at electrical grid development. In rural areas, there's also loads of activities in solar lantern and solar cooking, etc. So India really is a model for the world at the moment in terms of the rate of solar development that's taking place and the ambitions for that. But in a way it has to be, because of the demographic changes and the changes in wealth taking place in India. It has to change in that way, and it's pleasing to see that it is. So what's driving this? A lot of this is driven by this drop in cost of solar electricity. Over time, the price has been steadily coming down. This is grid electricity made from fossil fuels, and these will cross. And they've already crossed in many parts of the world. The sunnier parts of the world already crossed some time ago, and even less sunny places like Scotland, eventually the grid electricity will be more expensive. The fossil fuel electricity is more expensive than the solar, because the solar's come down in price so much. So that's happening everywhere. So what's the problem? Why do we need new technologies? Well, there's a couple of reasons why we want to go beyond those technologies. This is these silicon-based solar cells. You can have any color you like as long as it's dark blue. So the architects are not particularly taken with this idea of covering everything in blue rectangles. They didn't go to architect school for 5 years to learn how to put blue rectangles and everything. They want things more diverse. But also there's other contexts beyond electrifying grids for cities, 1.5 billion people with no access to electricity, etc. And other technologies might be better placed to address those markets rather than simply rolling out more silicon solar cells. So this is a technical slide. Brace yourself for some technical stuff if it's not your background. I just think it's important to have some idea of how a photovoltaic solar cell works in the simplest possible terms, just to have an idea of what people are talking about when you talk about different solar technologies. So here's a photovoltaic cell. In the middle we have an area, a material which absorbs light. Absorbs light to excite an electron. So the energy from the light will excite an electron. So this excited electron now has a lot of energy, and it can move into this electron conducting material and be transported to one of the electrodes, the anode. Now when you remove an electron which is negatively charged, negative charge, then you leave behind a region of positive charge, the absence of an electron, and we call that a hole because there's now a missing electron. And what we have on the sandwiched on the other side is a hole conducting material, so the hole is then conducted through to the cathode. So we've separated the electron and the hole. That creates an electrical potential, a voltage, and that voltage then can drive the electron round the outer circuit, doing some kind of work, lighting up a bulb or something, until it gets back around the circuit and recombines with the hole. Okay, so one photon of light in from the sun should lead to one electron going around the circuit, creating an electrical current. So that's basically how a photovoltaic cell works. All of them contain these basic elements. And when people talk about different technologies, silicon, cadmium telluride, copper indium gallium diselenide, what they're talking about is this absorber layer, the different materials that are used to absorb the light in the first step. So these are the well-established technologies. So silicon is more than 90% of the market. Silicon solar cells, the absorber layer is silicon. Cadmium telluride is also popular. Copper indium gallium diselenide, gallium arsenide, these make up most of the rest of the market. And these have a high efficiency and good stability. That's why they're used. By high efficiency, we mean maybe 20%, something like that, a power conversion efficiency of 20%. However, silicon uses a thick absorber. The silicon has to be a very thick layer, and that means they're heavy, they're brittle, they make these big, rigid panels that the architects don't like. They're not useful for portable power, they're hard to transport around, they're quite fragile. These technologies have a very thin absorber, so that's better. You can make flexible, thin film solar cells, but they all use elements which are either scarce or toxic. That puts limitations on the implementation of those technologies. So in response to that, there is a number of emerging technologies using nanomaterials, polymers, dyes, perovskites. And these technologies are inherently low-cost materials compared with these, and inherently low-cost printing production. These can be printed rather than using these kind of clean room, high-tech technologies. These can be printed in the same way that you might inkjet print or print T-shirts, for example. So they're very low cost, lightweight, flexible, colored, integrated, so easier to build into different building situations, portable, lightweight, flexible, robust, all of these sorts of things. So the challenge here is to try to match the efficiency and stability that these technologies have already achieved, but with all these advantages as well. So some of these different technologies are coming down the line very soon, and will be available to think about in the rural energy context as alternatives to silicon, basically, and might provide different opportunities for application that fit better with people's lives rather than relying on silicon. Here's some pictures of these sorts of emerging technologies, printing solar cells onto steel. So rather than having these big silicon panels, you could print directly onto steel, for example, integrate into devices like rucksacks with lightweight, flexible solar cells. So lots of different opportunities there. Some companies are commercializing these technologies. So, for example, Oxford PV was founded a few years ago. They're working on what's called perovskite solar cells. So the absorbing layer is a perovskite material, which I'll tell you more about in a second. This is the hot new topic in photovoltaics. And the reason it's the hot new topic is because these perovskite materials can now achieve efficiencies similar to the best technologies, around about 20%. So similar to the established technologies, but they can be printed from solution. So they have the efficiency of the established technologies, but they have the low-cost printability of the emerging technologies. And that's the first time that's been achieved. So that's a unique new opportunity that everyone's really excited about. Here's another company working in perovskite solar cells, Saula Tech, and they're inkjet printing. This is an inkjet printer. So they can print these solar cells just using an inkjet printer, which is then much, much easier than the high-tech clean rooms and high-energy processing that's required for silicon solar cells. So silicon solar cells are already cheap now. As I explained, the price has come down, and these could be an order of magnitude cheaper again. And that would really be a massive game changer in terms of solar power becoming just ubiquitous and available to everybody. So at the moment, they're focused on things like phone chargers, flexible cells, things like that, roll-up cells, but they're developing their market. They're not selling anything yet, but they're almost there with the technology. So this is an actual perovskite. Methylammonium lead triiodide is one of the key examples. And we're working on different aspects of this. New hole conductors, new electron conductors, and also lead-free absorbers. One of the disadvantages of the lead, of these perovskite solar cells, is that they include lead. And some people are concerned about the toxicity of the lead. Some people say there's such a small amount of lead we shouldn't care. Other people say, well, yes, but it's bioavailable, it's soluble lead. If you were able to print this from solution, because the lead is soluble, to make the solar cell, then it could come back out into solution again and go into the biosystem. So there's a debate about how worrying the lead is at the moment, but certainly it seems like it should be a worthwhile scientific challenge to try to achieve the same efficiencies, but without lead. So we've been working on lead-free absorbers. This is a cross-section of a solar cell made in my group. You can see the perovskite in the middle, also some hole transport material, some electron transport material, and 2 electrodes, just like I showed you. So the lead, is it a genuine problem? Maybe it is, but if it's not, it might be a regulatory problem, or even just a perception problem. People don't want to buy or manufacture things full of soluble lead. Some people in the literature have reported bismuth materials as an alternative. Up until last year, however, the highest efficiency was only about 1%. much less than the 20% that's been achieved with lead-containing materials. Last year, that jumped up to 4.3%. These people reported silver-3 bismuth iodide. So 4% is still low, but you can see the direction of travel is towards higher efficiency. So working on these bismuth materials rather than lead could provide, hopefully, the best of all worlds. And that's what we're working on. So we've been working on bismuth-based materials as well. Here's some pictures of molecular structures. You don't need to look at that if you don't like that sort of thing. But the key point is that we're working on bismuth materials rather than lead. Bismuth is non-toxic. It has similar chemical properties to lead, so it's an appropriate substitution, but it's non-toxic. What we're doing with our bismuth absorbers is we're working with partners in China. This is Yue Hu, my former student. She now works with this guy, Hongwei Han, and they are making these big perovskite solar cell panels. And they're working in a company which they have created called Wonder Solar. This is some of the Wonder Solar labs. They are printing these big panels. So another company that's commercializing these solar cells. These are entirely printed. Every stage is printed by screen printing. So screen printing has been used for hundreds, maybe even thousands of years for printing fabric, printing on t-shirts, etc. Now you can print solar cells by using this same methodology. You print a titanium dioxide layer, zirconium dioxide layer, and a carbon layer. This makes your electrode structure, and then you soak your absorber into this from solution. So the whole thing is from solution and printed. So incredibly low-cost solar cells are on the horizon. There's several companies now out there developing these things. We used our bismuth materials, and we got about 1% efficiency. So they're working, but we need to improve that. That's our bismuth material in red, soaked into this structure shown in grey. So that was last year we worked on this. Now we've got some better materials that we're working on as well. So that's really what I wanted to say about photovoltaics, and it really is to just give you a technology perspective, because I know many of you work in social science, economics, etc. Technology is changing incredibly rapidly, and what you think of now as photovoltaic cells, which is basically silicon, there's going to be new things available in the next few years, which will be revolutionary in terms of cost and also revolutionary in terms of flexibility, lightweight, robust, etc., in terms of how they're used. So lots of changes taking place there. Okay, so the final part of the talk I want to talk about is really the main theme I'm talking to people, want to talk to people here about, which is photocatalytic water purification. I'm sure you don't need this introductory slide. You all know about the water problem. World Health Organization says about 750 million people rely on unimproved water sources. That's about 70 or 80 million of them are in India. So that's the country with the largest single number of people dependent upon unimproved water sources. But it's a problem that affects all countries, not just developing countries or poorer areas. United Nations says in 15 years' time there'll be a global freshwater shortfall of 40%. We already see in Cape Town, in Southern Europe, in Southern United States, even richer places have colossal problems with water shortage and drought. And of course, climate change then adds an extra layer of complexity on top of that about how those resources will change over the coming period. A lot of this is captured in the Dow Jones Water Index, so essentially a measure of the financial value of water, which just keeps going up and up. So the financial value of water is becoming a commodity that's of high value. So all these things reinforce the need to keep developing technology for water purification. So how does the semiconductor photocatalysis work? So the first stage is exactly the same as for a solar cell. We have some kind of light-absorbing material. This labels here, this is called the valence band and the conduction band. Don't worry about that. This just means there's lots of electrons with this energy level. And if we have incoming light, labeled here as H nu, then that will excite an electron to a higher energy level. So an excited electron, and then again, there's a hole left behind. So just like in the photovoltaics, the first stage is you create an excited electron and a hole. In the photovoltaics, we use those to generate an electrical current, moving the electron around. In photocatalysis, we use those to do chemistry. So the first stage is the same, but the next stage is different. So in photocatalysis, we use these to do chemistry. This electron is high energy, it's excited. It's going to attack things. It doesn't want to be high energy. It's going to try and transfer itself to something else if possible. So it transfers itself to some kind of molecule, which we're calling A. A just stands for acceptor. It's accepting the electron to become A minus. The hole doesn't want to be an empty hole. It wants to get an electron back from somewhere else. And therefore, it rips an electron off a molecule D, D for donor, to give you donor plus. So we've initiated some chemistry through the high energy electron and the high energy hole. Now this acceptor here most typically can be O2 because water is saturated with oxygen from the air. That will accept an electron to become O2 minus. O2 minus is reactive. It goes on to react further. It makes hydrogen peroxide. It makes hydroxyl radicals. D here is most likely going to be hydroxide, which is present in water. We rip off an electron to give hydroxyl radical. So now we've generated all these species in blue. These are very oxidizing species, very, very reactive, collectively known as reactive oxygen species. And these will react with any organic matter that's present to oxidize it, basically to burn it, to incinerate any organics that are present. So the contaminated water contains organic molecules and bacteria. With the semiconductor, that's our material, photocatalyst, and sunlight, we generate reactive oxygen species which turn all this into carbon dioxide and water. So mineralize, destroy, burn all of the contaminating organics. So this is the context we're thinking about where this might be applicable. This final stage of incinerating bacteria and organics is appropriate after any other water treatment that was required. So if you need to do some sedimentation, do that first. If you need to do some filtration, do that next, and do this as a final tertiary stage of advanced oxidation processes. So when we visited this village, Ketchera in Maharashtra, this was just over a year ago I was there, they talked about, be something you're familiar with, how some of these villages don't have a system for handling water. All the wastewater goes to these ruts. The sewage water goes to seepage tanks from which it seeps. So it contaminates the water table. And then this is the well just at the edge of the village, which draws the drinking water back from the same water table. So there's no treatment. This context where there's no other water treatment at all would be highly appropriate for photocatalysis because we don't need any electrification. It's powered by sunlight, and the materials then if they're cheap enough can simply be used to purify water before drinking. So what things we need to think about? Well, the cost, obviously. You need low-cost materials, low-cost implementation. Do you need maintenance? That has to be simple as well. Do we need to recover the photocatalyst material? It's got to be used many times, so we need to have some way of recovering it. And also, is it versatile? It needs to act against all kinds of different organic chemicals and also bacteria. So these things have to be thought of. And of course, the system has to be robust. Now, if you look in the academic literature, there's lots of papers about photocatalytic water treatment. But there's a very interesting one just from last year by this guy who's active in the field. Photocatalytic water treatment, so where are we going with this? And what he's complaining about is the fact that the academic literature is full of impractical suggestions. And he says in this paper, it's time to stop patting ourselves in the back for laboratory successes. It clearly turned a blind eye on fatal implementation hurdles. So very many of the materials described in the academic literature include materials that are expensive or low stability, fragile, or powders that would be difficult to separate. All sorts of problems that really might make a nice academic paper where you did some lab studies, but you couldn't apply it in practice. So everything we've done over the past 2 or 3 years in this area has been aimed at making everything practical, or as practical as we can make it, so that the materials we develop could be used in the real world. So what are we doing? Well, we're starting with titanium dioxide. So titanium dioxide is the standard go-to material for photocatalysis. It's low cost, it's environmentally safe, it's non-toxic, it's good stability, it's a good photocatalytic material, has a good activity. But it has some problems. The first problem is it's white, which means that it's only absorbing ultraviolet light. All of the visible light is being reflected. Only absorbs UV light, which means it's wasting more than 95% of the sunlight that's hitting it, because UV light is less than 5%. So that's a problem. Second problem is rapid charge recombination. Here's our picture again. We excite an electron to an excited energy level, leaving behind a hole. The electron doesn't want to be at such high energy. The hole doesn't want to be without an electron. We want this to happen, but this electron could simply collapse back down under process 2 and refill the hole it just came out of. This is called recombination, and it just wastes the energy. That's what we don't want. But actually, you get rapid charge recombination in the titania. So that's a problem. It much reduces the efficiency. And the other problem is, if we use this as a powder, that powder would need separated. So now we have to have some kind of engineering solution. In some contexts, that might be appropriate, but we want to think about some of the most remote villages where there's no electrification, no infrastructure, no engineering skills. Then using powders is not going to be very straightforward. So this is some of the papers we published in this in the last few years. So how do we overcome these problems? Well, this slide explains how we overcome all of these problems. The first thing is we do everything immobilized on a film to avoid any issues of separation. So this is our catalyst. This is titanium dioxide, just pasted on and heated to bake it onto a glass slide. So it's immobilized. There's no separation problem. The second thing is we combine the titanium dioxide with a second material, in this case bismuth oxyiodide, and you can see this is red. This now introduces some visible light harvesting, extends the amount of light the material can absorb, and therefore the efficiency. And the third thing is that we add this as a surface layer on top of the titanium dioxide. So we have what's called a heterojunction. So we have two different materials with different energy levels, and it means that if we generate an electron here, it hops to the other material. And if we generate a hole here, it hops to this material. So the electrons in the hole are separated into two different materials, and that greatly slows down this recombination where they're present together in the same material. So all three of these problems are addressed by these immobilized heterojunctions. So this is titanium dioxide. This is with 3 layers of the bismuth oxyiodide. That's 5 layers, that's 7 layers. So we can sequentially modify this with another semiconductor to introduce the color and the heterojunction for reduced recombination. And what do we see in practice? This is first order kinetics, showing the rate of destruction of a model organic pollutant. TiO2, this slide here is in black. This one here is in red, and it's enormously faster at destroying the organic pollutant than the titanium dioxide is on its own under sunlight. So that's the key thing. We've massively improved the efficiency. This material, it turns out, wasn't stable enough. It's good for illustrating the concept, but it wasn't stable enough. So we moved on to other things for better stability. So we tried using carbon materials in combination with titania. So everything again is this heterojunction where we have two materials working together. So again, by a solution processing route, so we're not using any high vacuum, we're not using any lasers, we're not using any expensive equipment, we're just using chemical solutions and heat. We can make our titanium dioxide coated with a carbon material. This is the titania here. You can see a surface coating maybe of a different material here, a layer on the surface. That's our carbon material. And also doped with chlorine, which also helps the light absorption. This shows the uniform doping of chlorine into that material. So this was a different material we looked at, and we tested this against several different types of pollutants. 4-chlorophenol is basically a chlorinated organic molecule, which is typical of many organic pollutants. And this is our hybrid titanium carbon material here, showing that by far the fastest degradation of this pollutant compared with all these controls. The black one is titania on its own. This is bacteria, so our titania on its own under irradiation will kill bacteria through the photocatalysis mechanism. Our modified material does it much faster, so much more effective at killing E. coli. Actually, so something like chromium, you can't destroy an element. Okay, chromium is an element, you can't destroy it. It can't be broken down any further. What you can do, however, is change its oxidation state. So the chromium here is chromium 6+. So it has basically a nominal 6+ charge on the chromium. That's the one which is carcinogenic. That's chromate, which is carcinogenic. By photocatalysis, we can reduce it to chromium 3+, which is much less harmful. So we can't destroy it, but we can reduce its harm by photocatalysis. And again, our modified material is much faster than these controls. Now, the key question is, I didn't put the slide in, is it stable? This one is actually much more stable. What we're working on now is a material which works even better, which is a hybrid between titanium dioxide and bismuth titanate. Again, it's all solution process. We take titanium dioxide, we paste it on, make our film. Bismuth titanate is formed into this immobilized structure. We can do photocatalytic degradation of pollutants. We can do photocatalytic bactericidal activity. And this is what we want to do now. This is all lab work. Now we need to assess this in practice and see if it works in the field, in real people's real villages with real drinking water. Sample preparation. So in this case, we did this on glass slides and it worked like before, but we want to move towards a more practical system. You don't want to be using sheets of glass for photocatalysis in a practical environment. So we switched into beads. So we can buy these glass beads. I have some in my hotel room. I forgot to bring them with me today, but you can see them in the picture. So we have these glass beads, just a couple of millimeters across, and we can etch them, first of all, to make the surface rough, and then coat them with the titanium dioxide suspension and heat, and we get this. We get the photocatalyst coated on the surface of the beads. And then we can do our modification to improve the titania by coating on our second photocatalyst, in this case the bismuth titanate. So then we have these beads coated with enhanced photocatalyst. And all of this is done by solution processing. So in order to do the solution processing, we put our beads into some kind of column, and we do the chemical modification, first of all with bismuth nitrate. So this attaches bismuth to the surface. We rinse off the excess, then we use potassium bromide. That makes the bismuth oxybromide, and we rinse that off. So we deposit this bismuth oxybromide by this process which is called Sylar, which is just successively running these solutions down this column. So everything is solution processed. There's no vacuums, there's no lasers, there's no difficult equipment required. Then actually annealing of this converts the bismuth oxybromide into bismuth titanate, which then is our robust, stable photocatalytic material. We can do the photocatalytic testing, again in something like this, just by shining a halogen lamp. The halogen lamp has this spectrum shown in yellow, slightly different from the solar spectrum, but a close enough match for a decent first approximation. And we measure the degradation efficiency of pollutants. Again, we can use 4-chlorophenol. This is a chlorinated organic molecule that we used before as a model pollutant. If you have no catalyst, almost nothing happens. If you use titanium dioxide on its own, you get some degradation of this. But if we put on 7 layers of the bismuth titanate, we have the best photocatalytic performance, much, much better than the titanium dioxide. And this time it's stable. So this is the initial efficiency over a 3-hour period. 75% of the 4-chlorophenol is removed. Each of these blue bars is 3 hours. of reaction time, 3 hours of irradiation. It does drop. However, this dotted line represents taking the catalyst beads and heating them in an oven at about 400 degrees. And what that does is it seems to clean the surface, so the activity goes back up again. And it drops, and we heat them again. And you can see actually eventually it's kind of stabilizing about this level. Every time you reheat, you can get back up to about 65%. And it doesn't seem to be dropping anymore. Now, of course, ideally we would continue this on, but after 60 hours, I think the student thought he'd done enough. So we've at least shown over that time scale good stability under irradiation, with the occasional heating to recharge. Yeah, this is in synthetic wastewater. So this is just for chlorophenol in deionized water. So it's a slightly artificial system because we don't know if more heavily contaminated systems would still work. So using synthetic wastewater, we can see that we can still degrade this pollutant. So we know that using this basically as an indicator, and using that as an indicator, we can see that we have very good photocatalysis, and most of this is degraded in about the same time scale, with our catalyst much more enhanced over titanium dioxide. And for bacteria, again, it works well. So this is again using E. coli. This is the initial culture. This is with, after 90 minutes using titanium dioxide on its own. You can see the number of colony forming units left here, but using our modified material, it's almost completely gone. And on a log scale, this is log of the colony forming units. Our modified material is much superior. So we start off with about 10 million. The titania reduces that to somewhere in a few hundreds, maybe 300. And our modified catalyst is less than 10. So we can really make massive improvements using a stable material. Everything costs very little. Titanium dioxide costs almost nothing. You're almost paying more for the transportation than you are for the actual material itself. If you bulk buy, it's extremely cheap. It's used in white paint. Everything is painted with white paint. You can think about how cheap it has to be applicable in that context. Bismuth is also a cheap material. So everything is very low cost. The processing is low cost. The material is stable. It's immobilized. It's highly active. So really, in conclusion, this is going back to this paper that was published last year, photocatalytic water treatment. So where are we going with this? If you look at the literature, as I said, the majority of practical studies just use titania on its own, unmodified. It's not particularly active. We've improved that with modified titania. The majority of literature academic studies just look at decolorizing a model dye, which looks good. You can follow it by eye and with the spectrometer, but it really tells you nothing much about how that system will perform in wastewater or with bacteria or with other organic, more stable organic molecules. So that's a weakness. There's very, very few studies in the literature where people actually take titania, make it better, as we've done, and then study not just the organic pollutants, but also model pollutants, but also wastewater, also bacteria, also chromium. So we've really done a very complete study. There's very few studies like that in the literature. And again, then taking that type of material out into the field is almost nothing. So that's what we want to do next. So we've made these photocatalytic beads coated with this composite photocatalyst. The beads are our first suggestion, our first attempt. In the future, we want to try plastic. So you can have flexible plastic sheets with photocatalyst. We want to try metal mesh as a substrate for the photocatalyst. We want to try fabric. So we can work on all of these in the future. But right now, what we have are the beads. These are effective for pollutant and bactericidal applications and can be recycled and are tolerant to synthetic wastewater media. So we think we've really done something practical that could be applied in this type of context that I mentioned earlier, where people are just drinking untreated water from the ground, and some kind of treatment could make a big difference to that. We spoke to the people here, and we said, is the water bad? And they said, well, we don't know because we never drank anything else. So we said, well, what kind of ailments do you get? And they said, well, in the rainy season, everybody gets diarrhea. We have liver problems, we have kidney problems. Okay, right. So that's the water then. So clearly, any improvement to that situation would be advantageous. So this is the well. Maybe you can see the turtle in the well there. Final thing I want to just quickly mention, because I put this in at the last minute, because I noticed you also do outreach and education in A3. We've been active in outreach for a number of years. Through this project, the Solar Spark, this is our website, and this is a science communication project mainly aimed at photovoltaics, but now we're more active in photocatalysis. I want to introduce some photocatalytic outreach as well. And we do lots of different things, explanations of the science, experiments for teachers, videos, animations, and podcasts, etc. So here are some podcasts, various scientists talking about their work, and also some animations explaining how these solar cells work. So some of these have been viewed a couple of 100,000 times. So how do different solar cells work? This is all online, and we're going to be adding to that with scientists talking about other newer technologies. These are experiments for teachers or for the home, complete with instructions, how to do the experiment. All, of course, safe materials, low-cost materials, so that schools can afford to have them. Risk assessments as well, so that they can do the work safely. In some cases, we also have videos showing them how to do the experiment in case they don't have the confidence to do it themselves. So all these are experiments that can be done in schools. And of course, all of that's online. We want to have people-to-people contact as well. So these are some of my students out in a local library, in local PE hall, with various props and hands-on experiments talking about solar energy and renewable energy in general, and introducing the wider public, school children, adults, etc., to solar energy. So, you know, we're active in this area as well, if anybody wants to talk about that. So I'll just finish off with some acknowledgements. The work I spoke about at the earlier part, our work in bismuth absorbers for photovoltaics, has been done by my student Tian-Yue Li. Guylan Odling has developed all the photocatalytic materials that I spoke about. All of that work was done by one student. He's now in his final year, but I will have a new student through the hydronation scheme starting on the same topic from autumn this year. My colleague in engineering, Thalia Chatsisimion, is a water engineer, and we do the bacterial studies in her lab. She's also an expert on reactor design, that type of thing. Aruna Ivaturi was my postdoc, also working on photocatalysis. She's from Hyderabad originally. She now works she was my postdoc, but she now got an independent position. She's now working in the University of Strathclyde in Scotland, just 50 miles away. So we are still collaborating with her. Various people for funding, and I hope I managed to explain things in a way that was accessible. So thank you very much for your attention. Thank you.
Actually, two questions, but I'll ask the bigger picture question first, which is, you know, there's a lot of movement generally towards the world, towards this idea of design thinking, which is thinking about systems from start to end.
Yeah.
And I was wondering, I mean, it was interesting right in the beginning when you talked about your solar waste project as being quite separate from your design for the project. I was wondering if you had to think about the waste side of the whole equation, in the sense that if you had to say, how do I manufacture this, how do I get it to the field, and who's going to take the glass beads and where they're going to end up?
Yeah.
Would that end up with a very different optimization where you would actually end up with a different set of materials that you thought about from end to end, as opposed to optimize each piece separately?
I suppose intrinsically what we're trying to do from the outset is to only work with materials where the harm would be minimal. if leaked into the environment. So suppose somebody just throws their beads in, like out the window when they're finished with them. We wouldn't want that to happen, but if it did happen, there'd be nothing in there that would be of any intrinsic harm. The problem with the solar waste was specifically electronic waste, and electronic waste contains huge amounts of heavy metals, for example. In fact, one of my colleagues in Edinburgh works on what they call urban mining, which is where they try to recover value from waste. And what he tells me is that electronic waste, mobile phones, for example, contain about 50 times more gold per kilogram than gold ore does. So recovering, that's a different sort of thing where there's really harmful material in there, the electronic waste, that A, should be recovered and should not go in the environment, but B, actually has some value to recovering it. I think it's slightly different with these photocatalytic beads, where they've been designed to be innocuous from the beginning. And we might want to recover them in order to recharge them and reuse them, but actually at the end of their life, it's not such a concern.
So actually, the question came up when you were showing the solar, the printable solar panels.
Yes.
Which is where I first thought, I thought everybody else is kind of moving towards modular design, where you want to, at the end of its life, be able to pull out a piece of it and then disassemble them. This seems to be going in the opposite direction. That's the reason.
Yeah, I think that there needs to be some careful thought. So these lead halide perovskite solar cells have the potential to be ultra cheap, really a kind of step change, order of magnitude change in cost, and are fully printable. But they have this lead issue, and as I say, people are arguing about whether this is a problem or not. I think for me, if you're building a solar farm, so you install panels, there's a fence around it, you look after it, and at the end of its life you decommission it, there's no problem. But if you're going to start introducing solar technologies to rural areas, integrate them into buildings, exactly, then I think you do need to worry about what happens at the end of its life and whether you can control that. And under those circumstances, maybe lead's not acceptable. And then it could be that we have this fantastic new technology, which is super low cost, but actually the poorest people can't use it because of where they live and the fact that it's domestic use. So this may be why, this may be where bismuth, for example, alternative absorber that we're working on, might have a niche. Even if the efficiency is not as high, provided it costs very little and is stable and non-toxic, and you don't have such big environmental concerns, and maybe that could be used.
My question related to the lead issue. For example, on your roof, you have the solar panel issue related to lead. And the same solar panel, some people use it for generating electricity at the same time. Same solar roof is being used to harvest rainwater. So if we have rainwater harvest, will also be being done by some of the communities. And when you have lead issues, and then how do you tackle the pollutant pollution?
Well, this is really my point, is that I'm not sure that the use of that particular type of solar panel is acceptable in that context. And maybe that despite the many advantages of cost and efficiency, that it won't be permitted to be used in that type of context. So, you're right that would be a problem, and maybe it wouldn't be acceptable. So we can't just expect that one technology to be suitable for every use. We need to work on other technologies, such as the lead-free systems that we're working on.
There's so many people are trying to use the same roof, but they're making it from the solar panels, and also same roof for the harvesting of rainwater.
It's mandatory in India.
It's in India.
You have to harvest your rainwater.
You have to collect rainwater. Yeah. Right. Yeah. But this is what I'm saying. I don't think that kind of solar cell would be acceptable for that. So
this is not the commercial one.
that's no. Yeah. These emerging technologies will have appropriate niches depending on the exact nature of the technology, and that wouldn't be acceptable for that one.
I was just wondering, was there a reason why beads were chosen over any other geometric shape, or is it more efficient to use beads as opposed to say a rod painted with the same material? Or
We wanted beads for surface area, because obviously the only place the photocatalysis takes place is at the surface. So if you have you want to maximize the surface area. So a bead system is porous. The water can penetrate through the beads. So that's why we went for that. We wanted something which, because of course the best thing is powder, because then you have a huge surface area, but you have the separation problem. So we wanted something that maintains some of the aspects of powder by being a high surface area system, but with heavy enough beads that you can decant the water out without having to use a filtration system.
So probably a silly question. I was thinking, in future, do you imagine that right now, I guess you're baking the whole thing onto a glass and it requires high temperature. But you imagine it to be just like printing on materials. In case of water, it could be printed on vessels, the glass containers, and which would not take up space for the reason. So I was just curious about
So coating on the inside of a glass bottle would be another possibility. So then the whole bottle becomes the product, as opposed to making and distributing beads, which could go into an old plastic bottle that you just happen to have. Then the whole bottle becomes a product. Another possibility is on plastic. So if you coat onto plastic, the plastic could be rolled up, put into a bottle, and then it just takes the shape of the bottle. So that's another possibility. The thing is, my background is in materials chemistry. I really need to speak to somebody like my colleague Thalia, who's a water engineer, about mass transport and surface area and all these kind of things, because that's not my area of expertise. So we're just working on the methodology of coating beads, and we've done a bit of work on fabric and on metal mesh, which is a direction we can also try. But to be honest, I don't really know which is the best. Some compromise between surface area, optical penetration, etc., is going to be the cost is going to be the best, but we don't yet know what it is. I like to think about the what people in the software industry talk about minimum viable product. So if you've written some kind of app, for example, you don't sit in your ivory tower and spend 10 years trying to write the perfect app, and then eventually you release it, and it turns out that the world has moved on, or that it wasn't perfect after all. They don't do that. You know, what they do is they write a beta version, and then they send it out there, release it, and then all the early adopters will try it and give them feedback about what doesn't work, so then they improve it. So they talk about a minimum viable product. So something is good enough to do the job. It may have many flaws, it may be imperfect, but it's good enough to do the job. And by getting it out there and trying it, then they get feedback so that they can make it better. And what I hope is that we're at the stage where we have a minimum viable product, something that's ready to be tested, which is this glass bead system. It may not be perfect, there may be better ways to do it, but by starting the process of testing, that's what we find out, so that we can then continue to improve. And if it doesn't work well enough, okay, but we learn something, and maybe we have ideas for how to improve it.
So these beads, I mean, I don't have a science background. I was just trying to understand the beads which are at the center of this bottle, which are not receiving direct sunlight, they're just as effective as the ones.
No, exactly. So this is a limitation. So the beads, there'll be a certain penetration depth of the light. So what we'll have to do is have to basically lie a bottle on its side so that the beads spread out as much as possible. And the thickness of the beads, there's no purpose in making it too thick, because then only the top layer will receive light. So we need a kind of optimum amount of beads. So you have maybe 3 or 4 layers of beads coating this, just lying on the side of the bottle, and the light can come in, and then we'll see how well that works. Mm-hmm. We haven't done any field testing. No. Everything I showed you was in the lab with a lamp. Mm-hmm.
So one of the things that you mentioned is that after probably 4 to 5 trials, you would need to keep it once again so that it will activate it again.
Yeah.
So how would that be? Is it
So this is something we need to look at, because we don't know the minimum temperature that would be required to recharge the photocatalyst. We also don't know if the degradation continues. So if you don't do this recharging, you can see here maybe it's kind of settling down to a certain value, and maybe it doesn't keep dropping. And here also it's kind of hovering around a certain value. So you lose a bit, but then maybe if it stabilizes, maybe you don't need to do the heating. We found there was an improvement if you do the heating, but maybe it's not necessary. Maybe you can just continue to use it, and this will stabilize. Or alternatively, maybe we didn't really play with the temperature. Maybe the temperature of a domestic oven is enough. Or maybe it has to be higher. Maybe it has to be like a kiln for making bricks or something. We don't really know, but that's something that needs to be understood and tested. Mm-hmm.
Another question is, as you are developing this, you would have something in mind as to at what scale you would want water to be. You would imagine people doing it at the household level with water bottles.
Yeah. Yes. So
Buckets and pots, or do you visualize something at a group or a community level where you have larger quantities of water being treated?
Yeah.
At what scale that would be?
So I could be completely wrong, because I'm not the expert on villages, but my initial thoughts are a domestic scale, purifying water in individual bottles for individual use. So for drinking water only. So we're talking about the final stage, not the water for washing or anything like that, but water for drinking. That is a final treatment before drinking to remove bacteria and organic pollutants. So really on just the domestic individual scale. There's also, I think if you're talking about a centralized system, if you have a community where there's big enough for a centralized treatment system to be viable, then perhaps this is not the best way to do it. I think this might be the best way to do things if you have a community or houses that are too scattered or too small to justify a centralized system. Along the lines of the type of place that we visited, like this, where there's zero treatment because it's a small village, it's not electrified, there's nothing they can do. So that's the sort of context where individual treatment of personal drinking water by this process could make a difference. But there might be other, that's just my limited understanding. There could be other contexts that you know about where this would be appropriate as well that I don't know about yet. Mm-hmm.
I just wanted to say, off the top of my head, if I were to think about implementing this project in a village like this, for instance, I mean, and I'm sure you were aware of it, and all of us have had experiences that many a time people come with their ideas and new technology, they just sort of give instruction kits or little booklets in local language, or literally just drop packets into the sky and fall bricks. Somehow, somewhere, definitely something fails, right?
Yeah.
So if I were to think about implementing in a cluster of 15 to 20 households, it would require a presence of somebody who's someone who can talk to them on a daily basis or an everyday basis. There has to be constant feedback.
Yeah.
Not just a matter of training someone from those hamlets, but also literally somebody living there for months on end, trying to work with people and sort of taking down notes, and it has to be a very, very intensive field-led project. I were to think about it.
So the answer is I don't know, because I don't have a social science background, which is partly why I need to speak to social scientists. But for me, from what I have seen and what I'm familiar with, it seems like this type of thing has to become a business. It has to be somebody who's driving it, and to drive it, they ultimately need to be making money to make it viable. So that then provides the motivation for somebody to be knowledgeable about what the technology is doing because they're selling it. And it's not about somebody from the research institute or from another country coming and dropping off a parcel and going away again, or having to stay there for months on end. It's about somebody local who wants to do it because they can make money doing it, selling beads, recharging beads, and explaining the benefits. I don't know if that works or not, but it has to be that way. It has to be the community that wants to do it, and making it a business can make that practical, I hope. I think it's difficult, I think, if you're, as I said, the people we spoke to in this village, they couldn't tell me whether the water was good or bad because it's all they ever drank. So if people see improvements in health, maybe they start to learn that this is a good thing to do. But does that take too long? Do they sustain enough motivation for long enough in order to see those improvements in health? If you don't see how long before you see the reward, and do you keep going with the activity if you don't see the reward yet? Or if you get, this is what happens with inoculations, for example. People become complacent and say, well, we don't need inoculations anymore because nobody has these diseases. So people stop getting inoculated for rubella, for example, and then it comes back. So people have to keep doing it. And they're no longer seeing the change before they did it, after they did it. Do they just lose interest because it seems normal now that they don't have these health problems anymore? So I can stand here and list problems, but I'm not sure I know the solutions. Or maybe you do.
So again, one clarification question: when you see these beads have to be treated at a high temperature, is there a chemical process involved in it, or is it just direct heat? Like, what is the process in which these?
No, it's just heat. What we think is probably happening is that the surface is probably gradually accumulating some contaminants, and that by heating that we get rid of that. And
Is there then another way of treating these beads which doesn't?
Oh,
My only concern.
you might be right. Yeah.
Yeah, because only concern is when the treatment is at household level. The treatment of the beads is not decentralized; it's actually centralized. It has to go to a centralized unit.
Yeah.
The households can't keep the beads at home.
Yeah.
Then the solution is not entirely decentralized.
But then it could be some local business. The person that sells you the beads takes them back swaps them after a month and recharges them, for example.
Yeah, that would also mean that the economics would require that the technology required to treat the bead is not very high.
No.
Then otherwise they would have to sell the beads at a higher price to these households, and then I don't know as a business model whether that makes sense.
I don't know either.
Another way of treating the beads that can be done at household level, then this would be.
That's a good point.
Decentralized.
It's a good point. I like that question because it's ultimately a chemistry question. So I feel like we might eventually be able to answer that one. We haven't looked into it, but yeah, I agree with you. It could be that some simple treatment, just some washing protocol might do the same job, and then it would make it much simpler. Mm-hmm. Mm-hmm. Any more?
Okay, that's it. Thank you so
Okay,
much.
thank you.